What's up, everybody? So we are starting Unit 2, and it's important to know that the beginning part of Unit 2, we take a drastic turn in regards to the information that we're covering. So we're going from learning basic shapes and principles and abbreviations for geometry, and now we're getting a little bit more into the what's the word I'm looking for? More into the critical thinking aspect of geometry and how a lot of the what we call properties and theorems came into existence. So these next few sections are going to be very different than probably any math lesson that you've ever had before. And so there's not a lot of information, but it's definitely different information. So starting with 2.1, patterns in inductive reasoning. So I'm going to throw out a diagram and 3 numerical sequences here. So I want you to look at them and see if you can identify what the next figure in the pattern would be or what the next number is in the sequence. So maybe pause the video because I'm going to keep going on. So as you look at that first diagram, notice that we start off with 1 block. And in the next figure, we're adding a block to the top and to the right. And the next figure, we're adding another block to the top and to the right. So based off that theory, if we were to take our third figure, our fourth figure should add another block. 1 at the top, and 1 to the right. And then our fifth figure would add another one, and another one in each spot. Right? So we came up with that idea based off our observation of the previous 3 figures. Keep that in mind. Now let's look at our number sequence. So we go from 1 to 4 to 16 to 64. So based off of that pattern, what should our 5th number be? Well, let's look at what's happening. I'm getting 1 to 4, 4 to 16, 16 to 4. I'm multiplying each one of these previous terms by 4. So 1 times 4 is 4. 4 times 4 is 16. 16 times 4 is 64. So that means to get my next number, I would do 64 times 4, and I would get 256. And again, the reason I'm making this conclusion is based off the previous information that was given to me. Looking at our next one, -5, -2, 4, and 3. Well, -5 times like a decimal or a fraction will give me -2. But then multiplying that by 4 wouldn't really make sense because my number should keep going down, but my number's going up. So maybe I'm adding. So for -5 to -2, I'm adding 3. -2 to 4, I'm adding 6. 4 to 13, I'm adding 9. So based off this information, I think my next one, I would have to add 12. Each time I'm adding 3 more than the previous term. And then for our last one, I have 1, 1/2, 1/4, and 1/8. Well, to get from 1 to 1/2, I have to divide by 2. But I don't like thinking of it as dividing by 2. I like to think of it as multiplying by 1/2. Because to me, that's a lot easier to see. Because if I multiply 1/2 by 1/2, I get 1/4. If I multiply 1/4 by 1/2, I get 1/8. So if I were to multiply 1/8 by 1/2, I would get 1/16 as my 5th number in the sequence. So the big takeaway that I want to point out as we're doing is we got to all of our conclusions based off observing what was happening previously in the sequence. Okay, so first step, we were looking for a pattern. And then the second step was we were making what's called a conjecture. So that's a new vocab word for us today. A conjecture is a unproven statement based on observations. So one more time, a conjecture is an unproven statement based on observations. So it is a conclusion, but it's a conclusion in a special way in that we reached it by observing what was happening. All right, but nobody told us anything. There's no facts to go on. It's just we observed something happening, and we made what's called a conjecture. We figured out what the pattern was. Now, this thought process in purple, looking for a pattern and then making a conjecture, that is called inductive reasoning. So inductive reasoning is making a conclusion based off observation. Now, we'll talk about why that's important at the end of the notes, but I want you to think about a lot of the things, especially right now, like with the way things are in society, is like inductive reasoning plays a major role on a lot of the things that you believe, specifically the formation of stereotypes. So stereotypes are conclusions based off of people, conclusions made about people or a race or a group, strictly based off of observations of things happening, right? And I'm sure you guys can all think of stereotypes that are out there about races, genders, whatever, right? And those stereotypes are conjectures, quote unquote, that are made by people observing that behavior or that belief. Now, are those stereotypes true? Most stereotypes are absolutely not true. But that is how they've come around, is because people observe something happening, they use inductive reasoning, they make a conclusion based on an observation. All right? And so inductive reasoning plays a huge part in today's society. That's kind of what I want you to understand. And I also want you to understand it as a math point. We'll talk about why it's important at the very end of the next slide. So here is how a conjecture becomes true. It has to be true 100% of the time. So as I said previously, stereotypes are never true 100% of the time. So every stereotype is a conjecture that is false or is not true, because in order for a conjecture to be true, it has to be true 100% of the time. So how do we prove a conjecture false? It's actually really easy. To prove a conjecture false, you only need to show that it's false once. So if 99 times it's true, but that one time it's false, a conjecture is considered false. And when we prove that it's false, that example that proves that it's false, that is called a counterexample. So a counterexample disproves a conjecture. And so when you think about this in the math perspective, I want you to think way back into Greek, Roman, the early ages of man, and when math started to become a thing, they started to build structures and plan out roads. They knew how to count, but there wasn't so much a formula book for them to look at. So they had to start looking for patterns. They had to start making conjectures based off things they noticed. So if it was true, it was true, but then it was false, that disproved the conjecture that was made. That was the counterexample. So they maybe had to throw away whatever that theory or that idea was that they're trying to apply in a mass way to numbers. So let's look at a more simplified version. Let's look at something that we can understand from an algebra perspective. Let's say that for all numbers x, so imagine any number for x, the expression x squared, so if we were to square that number you were thinking of, it's always going to be greater or equal than to the original number. So for example, if I take the number 2 and then I square the number 2, that gets me 4. So 4 is obviously greater than 2, right? So that's our conjecture. For any number x, the expression x squared is greater than or equal to the previous number. Right? So again, if I used 7, well, if I square 7, I get 49. 49 is greater than 7. However, I think we're all thinking the same thing. There's lots of numbers that we can use that when we square them, they are no longer greater than the previous number. That's one that hopefully jumps out to you right away is what if I square a negative number? If I square negative 2, that becomes 4. 4 is greater, let me rewrite that for you real quick, negative 2, and then I square negative 2. 4 is greater than the previous number, right? But that actually doesn't work either because 4 is positive negative 2, so that doesn't work. So what's another number? Anytime I square a negative, I get positive, so that's going to be greater. So think about what's another way. What if I squared 1/2? So 1/2 squared becomes 1/4. Well, 1/2 as a decimal is 0.5. What's 1/4 as a decimal? 0.25. So in this instance, 1.5 is greater than 0.25, so this would be a counterexample that disproves that conjecture. All right. So again, you only need one counterexample to disprove a conjecture. So as I said, guys, why is inductive reasoning important in mathematics? And it kind of goes back to the foundational when geometry was first coming into existence, right? The study of numbers. Most of the formulas, the theorems, the properties, everything that you're kind of told as a definition, that all started or had roots in a conjecture. People were working with numbers and they start to notice things, they start to notice patterns, right? And then they start to study them over and over and over again. And eventually they find maybe that they're always true, or maybe that there's one time it's false, so they kind of have to throw it out. If they were proven to be true, they ended up what's called becoming properties or theorems. These are going to be two big words that we use throughout the year in geometry. So like we know for a fact that they're always true. Okay? So inductive reasoning, the process of making a conclusion or a conjecture based on observation. Now you have a pretty short little worksheet to do. There's not a whole lot of new information. You're going to be looking at some patterns, trying to find the next number or the next symbol. You're going to be working with some equations, and then finally you'll be doing some counterexamples. Hope everybody has a good weekend.